Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Started then, so it's my great pleasure to welcome Wenzel Jakob here. Wenzel is currently in the computer graphics group in the ETH Zurich, and he did his PhD in 2013 at Cornell University. He has worked on a lot of different things, mainly in computer graphics, in realistic appearance modeling, in advanced Monte Carlo methods for rendering. In fact, he's the author of a quite impressive physical-based renderer called Mitsuba. I'm really happy to have him here and listen to what he will be talking about.
Thank you. So let's see if this works. Okay. Before I tell you about my work, I want to start off with a sort of a bird's eye view of the whole field of computer graphics. So as I'm sure you know, the twist of graphics compared to other types of CS subfields is that we're dealing a lot with visual data, and oftentimes that visual data comes from a physical object. And one thing that we can do is to acquire this information and then to fabricate a replica of the object. But another thing that we can also do is to process this information, so to transform it and to display it and then turn it back into a physical object. And there are various types of visual data, and in this talk I'll focus on what I think are the most important three. And those are raster data, so things like pictures or bitmaps, then geometry information, so triangle meshes, point clouds, and so on. And then there's also material data, and that characterizes the way in which an object reacts when it's illuminated. So let's take a look at this pipeline that I mentioned just before for these three different types of visual information. So for raster data, acquiring it is easy. I just take a photograph. That usually takes less than a second. And then for transformation, thanks to very fruitful research over the last years, we have a very mature software market, even software that caters to non-experts that can do all sorts of transformations. Displaying it is also very simple. I need a computer with a basic graphics card and a screen. And then fabrication, if you want to think about it that way, means printing an image. And what's important about this row is that all of these devices are available quite cheaply. And so this pipeline is just incredibly common. We don't even think of it as such. Now let's look at geometry data. Here, the capture stage gets a lot more difficult. So acquiring this information takes minutes to hours, and there are a variety of different devices that can do this. They range from structured light scanners to laser scanning depth cameras, multi-view reconstruction. But one serious issue of these types of techniques is that materials they interfere with the capture process. And so in this case, for instance, we had to apply some chalk to the owl to be able to get a decent reconstruction. And that's actually kind of tricky to remove afterwards. And then also these devices generally just provide the geometry. And at the very most, they provide a crude approximation of the material, such as the overall diffuse color. There's also a big software market based on the field of geometry processing, but this software is now much more complex and requires years of training to be proficient. And for displaying this type of information, now we need a fancier graphics card with 3D acceleration. Fabrication has really gone through the roof in the last years thanks to big progress on this 3D printing technology. So here are just a few pictures I found after Googling 3D printed bunny. And those are just silly examples. But the point I'm trying to make is that the moment that you have reasonably cheap devices that can kind of give you this end-to-end pipeline and a software market, then it allows people to be very creative. The example on the bottom left is a bunny sprinkler that shoots out water through its eyes. So on a more serious note, whoops, sorry about that. On a more serious note, this kind of technology can also really improve people's lives. So for instance, to design custom prosthetics for patients. Now let's look at material data. So to capture the appearance of an object, basically we have to illuminate it from many different directions and then also look at the way it reflects light as seen from different directions. And that's normally done with a machine called a spherical gantry. So this is a very specialized device. It's not something that you can order in a catalog. Usually you have to build it, and it's extremely expensive. Scanning this information takes much longer now, so definitely on the order of days to multiple days. The moment that and I should also say, these machines usually, because the measurement takes so long, you have to install them in a room which has dampening from vibrations, and it's also painted black to minimize the effects of the environment. So it's a fairly laborious measurement setup. And then to take this visual data and to turn it back into an image, we have to do a light transport simulation, and that's what's referred to as physically based rendering. And the computational costs of this step are outrageous. It's something I'll get back to later. And then transformation and fabrication is where it gets really sketchy. This is sort of the wild west of visual information processing pipelines. So there is some initial research, but I would say it's fairly crude. So for material manipulation, for instance, the state of the art is that you have a model with a lot of parameters, and then you can tweak some of them, and you get a quick feedback, and then people are generally pretty happy with that. But this is very alien to a person who works with materials on a daily basis. So think of a craftsman or somebody working in the fashion industry. It's just not the way they think about materials. So if I wanted to summarize my research goal in one sentence, then it's basically to make this last information processing pipeline work better on the order of the previous two. And I've been working on all aspects of that. And in this talk, I'll mostly focus on the display part, so physically based rendering. And I'll also briefly talk about acquisition and transformation, but no fabrication. So just a bit more motivation. Why do we care about materials and correctly modeling the physics of light transport? One reason is that the pictures you get out of it look staggering and realistic. And with careful modeling, we can make something that's really indistinguishable from photographs. And that's, for instance, why the movie industry is interested in them. And for predictive rendering and industrial design, the goal is to know exactly what something is going to look like before we make it, because doing so may be quite expensive. And for architecture, it's pretty much the same idea, just at a larger scale. And then for cultural heritage preservation, the idea is that we want to completely capture the visual data of an object because it's fragile and it may not survive to the coming generations. And so all of these applications share an extremely high demand on the realism, which requires accurate modeling on the material level. So I mentioned before that rendering is expensive, and just to truly communicate the costs of this step to you, I wanted to share an example from the movie industry, from the movie Gravity. So Tim Weber, who was the visual effects supervisor on this show, said that if they had just had a single machine to do their rendering, they would have needed to start at the dawn of the Egyptian civilization to finish rendering frames in time for the release of the movie. Now, if you're making a movie that will gross $500 million, then obviously that's not what you do. You take some portion of that money and you go buy a big cluster and shorten time that way. But this also means that this sort of technology is basically unavailable to most people. So to understand why these computations are so expensive, I'll briefly recap the mathematical problem that they solve. So here's a picture of a Cornell box, and that's sort of a standard scene that people use to reason about light transport. And let's suppose that we're trying to compute the pixel color of this black dot, which is moving back and forth on the ceiling here. Well, on the right side, you can see the corresponding computation. And essentially what we have to do here is to compute an integral of the incident illumination as seen by the black dot and a material term. So this is what kind of characterizes the way that this surface here at the top reflects light. Now this is a metal surface, and what you can see is happening here is that it selects out a narrow portion of the illumination, which leads to this concentrated reflection. And it's also dependent from which position I look at this point, and that's why it's also changing here. So normally, the way that we solve these kinds of integrals is Monte Carlo integration. And so the idea is that we take this integral, and instead of evaluating the whole thing, we just replace it by one or more samples. So we pick a point somewhere in the domain, evaluate all the terms, multiply them together, and then we just take that as an approximation of the integral. So let's say we just do one sample. Part of the problem here is that we don't actually know what the incident illumination is yet, so we can really just sample this material term. And so let's do that. Let's put a sample there. Then we also have to evaluate the unknown incident illumination at the same point. And so how do we do that? Well, this point here is actually a direction as seen from this point, and it's looking at another position in the scene. And so tracing a ray into that direction, we can find where that position is. And then we'll have to solve yet another integral as seen from the perspective of the blue dot. And so as you can see, this leads to a recursive algorithm. And that's also what makes it challenging. To be able to terminate here, I'm going to need to find a way eventually to make it all the way from the light source all the way from the camera to a light source through some number of intermediate bounces. And for challenging input scenes, this sampling problem becomes very badly behaved. So ultimately, what these methods do is to construct the trajectory of a light path segment after segment, which is actually a lot like they happen in physics. And I'll refer to that as the path tracing paradigm. And there are two main ingredients to build a working system on this paradigm. The first one is the rendering algorithm, and that's the part which is responsible for computing integrals, and it reasons about light transport. And the second one is the physical model, and this is all about the material that things are made of. And progress in both of these fields has been rapid, but mostly separate from each other. So people usually choose to work on one area or the other, but not both of them at the same time. And this is very much visible in the standard pipeline that people use for physically based rendering. So we have black boxes for the rendering algorithm, which is called the integrator here, and then for the materials and the geometry. And these communicate with each other through standardized operations, such as finding intersections against the scene geometry, querying the material models. And then more recently, it's also become popular to use Markov Chain Monte Carlo together with this. Then we have yet another black box that controls these other black boxes. So if we put on our CS hat, then this is actually a really nice architecture, because we have all of these well-chosen abstractions, and then we can, for instance, remove one of the black boxes and replace it with another one. And as long as it satisfies the contract, then we still have a working system. So it's looking pretty good from that point of view. But the issue is that there are many situations where complex interactions between these different parts lead to poor performance. And as a field, graphics has almost codified this particular set of abstractions with all its problems, and people rarely touch them because it's just such a big amount of work to make substantial changes here. So the issues that people normally get when there's a lack of convergence are noisy and unconverged renderings. And I'm showing examples for a few different methods here. And those images look pretty bad as single frames, but what you have to realize is that this noise is different in every frame, so it's much more distracting. And all of these methods, because they ultimately rely on the path tracing paradigm, they perform a random and brute force simulation of light path. And now the funny thing is that nature actually uses the same algorithm. So on a sunny day, about 2 times 10 to the power of 33 photons hit every square meter of the Earth and bounce around happily. And on the other hand, the fastest computer systems can do only a few 100 million rays per second. So we're really not going to win this if we'll go the way of brute force computation. And so I showed you how this traditional architecture is ultimately designed for this brute force approach. And so you can think of my work in this area as opening up some of those black boxes and seeing if there's something that we can change about that. And more specifically, I'm interested in developing models that can describe complex optical phenomena to give them the necessary smarts about the problems they have to solve. And I also want to understand the interdependencies between different parts of this pipeline and to find more suitable abstractions that avoid these low performance situations. And so I'll cover several projects that fit into this rough pattern I just described, starting with work on appearance modeling and then moving on to the rendering algorithm side. And the appearance models, particularly the first two, describe fairly specific physical effects that were essentially unrenderable with state-of-the-art methods, in the sense that you may have to wait a month or a year to get even a single picture. And so the focus here is very much on performance. And the first topic I'll cover is a specialized reflectance model for rendering glitter. Now, glitter is a phenomenon that characterizes many materials in our world. And when we look at them under the sun or a similar source of directional illumination, we see many small glints instead of a smooth highlight. And what's interesting about these materials is their behavior when we illuminate or observe them from different directions. So here's an example from a very common material that we don't normally think of as being particularly glittery. It's an injection molded power adapter. Like, I'm sure many of you have probably at least 5 at home. As the light source moves, what you can see is happening is that parts of the surface light up, and then they stay bright for a few frames, and then the highlight disappears again. And that seems to happen in an almost random way. Now, it turns out that most rough materials actually look like this when we illuminate them with a small light source like the sun. And the reason for this effect is surface structure. And that,
sorry, just to be clear, that was real?
That was real. Uh-huh. Yeah, you can do it on your own also. Just take a small light source and one of these power adapters. They have this grainy surface, and so you just need a small light source, and then they look glittery like that. Or take them outside. So the reason for this effect is surface structure, and that structure is usually classified into 3 different scales. We have the macro scale, that's sort of the size of things that we reason about in our daily lives. Then there's the meso scale, and that's where small surface variations and scratches are found. And then there's the micro scale, and that scale is so small that we can't usually resolve things anymore, even though they may still have an effect on the appearance. Now, in graphics, we have very good tools for dealing with the 2 extremes. In the end, that's the purpose of geometric models and the reflectance models. But the mesoscale is fascinating because this is where materials and the geometry meet, and we can still see the effects of this with our eyes. And this is where glitter occurs. So how can we visualize things at this scale? Suppose this is a tiny piece of surface that's visible through just a single pixel, and now our task is to compute the brightness of that pixel. Essentially, what we have to find out is how much of the surface is oriented in just the right way so that it reflects light from the light source, so for instance, the sun, to the camera. So how do we do that? Well, it's going to depend on where the sun and the camera are. And in reality, of course, those are much farther away from the surface than I'm showing here. So one option would be to use this path tracing paradigm that I mentioned before. And so to do that, we'd basically be shooting many rays from the camera, and then we just count how many of them end up at the sun. But the issue with this is that it's a terrible sampling strategy. The probability to hit the sun under these conditions is about 10 to the power of -5. So to really have a good estimate, a reliable count, in the end, we'd need to trace millions of rays per pixel. So this is not really going to fly as a rendering technique. On the other hand, we can think about the geometric situation here a bit more. So I showed you the surface where the sun and the camera were at a 45-degree inclination with respect to the surface. And under this situation, I think you can convince yourself that the only places where light can actually reflect are the ones where the surface normal points straight up. So the techniques that I'll mention now are based on this concept that we can build a sort of a database of where spatially and directionally things are pointing on a surface, and to query that database to prune down this big search space, and that we don't have to rely on this brute force approach. So we built 2 different methods. The first one is procedural, and it creates plausible glitter effects using a statistical model of microscale roughness. And the advantage of that is that it's very fast and requires almost no memory. And the second one is data-driven, and that can be used to visualize structure that has been measured or computed in a simulation. So here's a video from the first model, which creates plausible structure. And this is a pair of shoes illuminated from the left side. And what you can see is that we recreate this effect of glints appearing, persisting for a few frames, and then disappearing again. Here's another example where we show the effects of the parameters of the model to achieve, for instance, a different spread of the highlight. The data-driven model is slower, but it can be used to render more interesting effects, such as cutlery with scratches and dents. And we can also animate this mesoscale structure, for instance, based on the properties of waves to create realistic ocean views. And what you have to keep in mind here is that the underlying geometry is just a plane. So everything you see here is happening inside the shading model. And just to give you some idea of how long these images take to render, here's a metallic test object rendered once with our technique and then with the brute force method. And both images are noisy, but the noise on the left, those are the glints, the actual thing that we wanted to render. And the noise on the right is a performance, it's a convergent artifact of the brute force method. Now, using the order of convergence of these methods, we can estimate that it'll take about 2 years for the image on the right to converge to the one on the left. And that's just for a single image and not even an animation. And so this kind of database lookup approach is one way that we can visualize certain effects such as glitter. But now I'll switch gears a bit and tell you about another one for materials that consists of multiple layers. And this was published recently at SIGGRAPH. And the description of this project really begins with a personal anecdote. So in my spare time, I developed this Mitsuba rendering system, which is basically a simulation environment to compute realistic images. And at some point during my PhD, I just became really unhappy with the material system in it. So the part that's responsible for describing the reaction of objects to light. And I just wanted to redo it from scratch. And so I implemented first the really basic materials, which are things that conduct electricity and those that don't. And so you can use the ones on the left to simulate metals and those for non-metals like glass, water, air, etc. And I also made smooth and rough versions. And the smooth ones are called specular. That's a term I'll get back to later again. And I also had a basic version of a diffuse material. And then the next thing I really wanted to add were plastic-like materials. And those are characterized by having both a diffuse reflection and then also the reflection component from a dielectric. So how do we get that? Normally, or very often, what people do is that they make a blend. So they say, for instance, let's take 60% of the dielectric reflection and 40% of the diffuse, and then we'll just add them. But that doesn't even make sense. You can't just add these models like you would mix two buckets of paint. So a more sensible way is to devise a structural model of a material that will give you this type of reflectance behavior and then work out on a piece of paper or so what's the resulting equation that we have to simulate. And so here's an example. Here we have a diffuse base layer, and then we put a coating on top. And so that'll give us this kind of plastic-like appearance. So then, because let's see what happens when we shine light at it. Well, a portion is going to get specularly reflected, and then another portion gets refracted into this lacquer layer, and it gets diffusely reflected at the bottom. But now something also happens that we didn't originally plan for, which is that as light reflects back up from the bottom layer, it can actually happen that it doesn't escape immediately, but it gets reflected back down and interacts with the diffuse surface at the bottom once more. And this is actually what happens to over 50% of the light that gets reflected back up here. So it's a fairly important effect. Now, what we have to do is to integrate over all possible ways that light could take, and that'll give us some formula that we can plug into our rendering system. And it looks fairly complicated here, but it turns out that when things are so simple, I have these perfectly flat layers, perfectly diffuse bottom layer, perfectly smooth dielectric coating, then you can just do it on a piece of paper and work out the equation yourself. the effects of that are interesting. So if you've ever put a shiny varnish on a material like wood, you'll have noticed that it looks darker and more saturated afterwards. And the reason for this effect is exactly what I showed you on the slide before, that light can interact multiple times with the base layer at the bottom, which increases the amount of absorption. And if we simulate materials using layers, then we can recreate these effects. You can see that on the right here. So when I saw that, I got really excited, and I wanted to put layers on everything, also on metals and other types of materials in Mitsuba. But the problem is it doesn't work, because you can really just get an analytic solution for the very, very, very simplest case. And so this next project was born out of this search for a nicer solution to this problem. So this is basically a system to arbitrarily layer anything on top of anything and compute things while accurately accounting for all the internal reflections that happen inside the material. This is sort of a high-level overview of the system. So the user is presented with a graphical interface to design stacks of layers and to modify their properties, and that produces a structural description that's handed into a pre-processing phase that writes a file with coefficient that's read by a rendering algorithm, and that makes an image, which is shown inside the user interface, and so on. So I'll start by explaining this portion here that does sort of the main computation. And to motivate it, I'll start with something much older, and that's glass plates theory from Stokes. And I'll just discuss the version with one glass plate to motivate what's happening inside this algorithm. So suppose we have a flat glass plate and we illuminate it from the top. Then some portion of the light will get reflected, some portion gets refracted, and then like we saw before, there's another portion that kind of gets trapped inside the layer and it just bounces back and forth. And after every bounce, a little bit can escape at the top and a little bit can escape at the bottom. Now suppose that we wanted to know more overall what's happening here. So let's say we want to know the total amount of light that leaves on top. So we have to add up all of these arrows, basically, and then the total amount of light that makes it out at the bottom. Well, to do that, we have to basically compute the sum. So suppose that after one reflection event, the amount that gets reflected is called R, and then the amount that gets transmitted is called T. Then to compute this arrow, well, that's just R. And to compute the next arrow, it's T for a transmission, then R for a reflection, and then T for another transmission. So if we add up all of those arrows in this way, then what you can see is that we get a geometric series. And that's really nice, because whenever we get a geometric series, we can just directly write down an explicit answer without having to do the sum. So even though what's happening here seems kind of daunting, we can actually characterize it in a very satisfactory way. Now, with that example in mind, let's generalize a little bit more. So before, we had a glass plate, and we illuminated it from a single direction, and then we had an R and a T coefficient that kind of describe what's happening. Now suppose we have a thicker layer, and instead of illuminating it just from one direction, we're illuminating it from many directions. And because we want to compute things, we'll discretize that incident illumination into some vector of measurements. And that layer now, it doesn't have to be made out of glass anymore. It can really be anything. Let's think of it just as a black box that's hit by some light. Now, when light hits it, then some portion is going to be reflected and some portion will be transmitted. And this is ultimately a linear process. And so what it means is that we can describe everything that's happening here as a matrix vector multiplication. So the difference between what we had at the bottom here is that we're dealing with scalars, and then at the bottom, we're dealing with matrices. And now we can ask a very similar question, which is, if we have two layers, and we can fully describe what's happening inside them using matrices, and then we just kind of pack them on top of each other, are there also some other matrices that describe the combination of these layers with all the internal scattering that's happening inside between them? And the answer is yes. And the equations look a little bit more complicated, but if we compare them to what we had just now, you can see that it's actually kind of the same thing. So instead of a scalar division, we have matrix inversion. The constant 1 gets replaced by the identity matrix, and so on. And then some things didn't quite simplify so much because we're dealing with non-commutative matrices. But basically, yeah, those are the same equations, and they give us this very powerful operation to combine the matrices of any two layers and then figure out what the combination of them does. And this is basically what the main algorithm of this method does. So it takes a structural description of a layer and then just walks down from top to bottom and applies these equations over and over again. So this is the core operation in a system that assembles these layered materials. And these equations have been known for a long time, so we didn't invent them. But they're usually not practical for these kinds of applications because the matrices get way too big too fast. And our contribution here is a frequency-based representation that makes it possible to do all of this linear algebra in a sparse way to keep it efficient. And then we also show how to take a variety of standard models that people are used to in computer graphics and to project them into the spaces so that they kind of fit into this funnel. So there's lots of fun math in all of these boxes, but it's a little bit too low level for this type of talk. So I'll move on to the next topic now. For rendering, what we have to do is to satisfy the contract of one of these boxes. And for this particular representation I alluded to, it turns out that we get a lot of mileage from SIMD, in particular Intel's AVX instruction set. But otherwise, the rendering algorithm is fairly standard. And then after rendering, the resulting image gets passed back into the layer design interface. So here's a short demo of what that looks like. The user starts by adjusting the roughness of the top layer of a coded gold dragon and then add some scattering particles into this coding. And then after a pre-computation and a brief rendering step, the effect of this change becomes visible. Now I'll show some example videos of the same rough gold dragon with the clear coating. And what I'll do is I'll have two layers, the coating and the gold, and both of these have a roughness parameter. And so now what we can do is to tweak these roughness parameters independently of another. So here's what that looks like. On the left is the combination of those two layers, and on the right are the layers rendered individually. And here you can also see a structural description of what's happening here. So now you can see that the bottom layer is smooth, and I'm changing the roughness of the top layer. So there are some highlights here on the specular object that are basically being added or removed here. But then what's also happening is that the refractive coating blurs out the reflection from the metal underneath. Now let's do it the other way. I'll have the top coating be smooth, and then I'll change the roughness of the bottom layer. And now, as you can see, the effect is much more dramatic. And what's happening here is that the change, it becomes magnified by the refractive coating. That's why it looks so exaggerated. And then when the bottom is rough and we tweak the top roughness, the effects are much more subtle but still visible. And I'm excited about this method because it allows us to explore these types of interactions between different layers that previously just weren't feasible before, in the sense that you may have to wait a week, a month, or a year, depending on the parameters to render your image. So in practice, people just never use these kinds of layer combinations. And these, for reference, they took about 8 minutes per frame. Now, I don't have time to go into much detail, but one thing we also did was to investigate real-world layered structures focusing on enamel samples in jewelry design. So we manufactured a set of enamel samples, you can see one here, and then put it into a robotic gantry where we could move the light source and then take lots of pictures of the object at different light source positions. That gave us some measurements, those black dots, and then we fit a low parameter version of our model with just 3 parameters to it. And then we manufactured a flower art piece by 3D printing a wax model and casting it into gold. And then we coated it with the same sets of enamels that we had previously measured. And that made it possible to compare photographs and renderings of the final object. And here you can see what that looks like. So in this particular object, there's a color shift depending on the thickness. And well, the physical object has a sort of handmade quality because it was actually made by a traditional goldsmith who applied the enamels with a brush. So the estimates on the thickness of some of these are a little bit sketchy. But overall, I think that we were able to capture the salient effects here. So seen from a high level, the layers of this project and then the mesoscale from the last project, those were geometric properties. And all parts of this combination of black boxes had to work hard together to solve the problem in a brute force way. And with our modifications, what's basically happening is that they become the full responsibility of the material system. And then we also already solve a part of the integration problem in there, which makes it easier. The last appearance model I'll discuss is about rendering volumetric materials such as cloth. And this developed over a sequence of SIGGRAPH papers, starting out first with a general framework for volumetric light transport, and then later more specific applications to cloth rendering. And the motivation for this project was that there are just many objects in our world that reflect light in an interesting way as a consequence of their internal structure. So light enters these materials at some point, leaves somewhere completely different, and the path that it took depends on the geometric layout of what's inside. And these materials are also, in a sense, fuzzy, in that there's no clearly defined surface. Now, in computer graphics, if you wanted to render something like that, you'd use normally a standard framework that is known as volume light transport. And in this framework, there's a density function at every point in 3D space that roughly tells you how much stuff there is. And that works great if you want to simulate steam or smoke or the atmosphere of a stellar body in atmospheric optics, but it really doesn't work for these types of materials that I just showed you. And the reason goes back to the 1940s, where these equations were derived in the radiative transfer community. And back then, people introduced some critical assumptions to make the equations as simple as possible. And so in particular, they assumed that the medium is invariant under rotation. But this is obviously not true as soon as the structure of the material is oriented in some coherent way. So suppose we are dealing with this medium that's made out of ellipsoids that point primarily in the upwards direction, and I'm visualizing evaluations of the extinction coefficient, and that quantifies how much light scattering there is. And you can see that clearly it's much more for light that's coming from the left to right versus light that's coming from top to bottom. So this is a medium that violates this assumption. And so our work in this area was to develop a new mathematical foundation for light transport that still works for these types of materials. And then we focused particularly on media containing fibers. So I'll show you one of the first visual results we got using this theory. This is a scarf created from a physical simulation by Keller et al. And with the classical theory, we could only ever render diffuse-looking fibers. But in the real world, fibers reflect more light into some directions than into others. And there are also chemical processes such as mercerization to further increase the shininess of fibers. And in this image, we can capture these sorts of effects after generalizing the underlying theory. And this result got us excited, and we wanted to test our theory on other types of oriented structures. But a big impediment then was just how can we get good data to feed into our algorithms. Later, we sent tiny pieces of cloth to the CT scanning facility of UT Austin, and they acquired these incredibly high-res 3D scans for us using micro-CT technology. So this is an example of velvet. And then the second one is for satin. So once we've scanned a particular cloth sample, it's possible to synthesize more of it procedurally in a computer simulation and use it as an input to our method. And in this way, we can reproduce the appearance in rendering that convey both the character and the detailed structure of different weave types. And what's interesting, and that was sort of one of the main points of this project, is that we can scan different weave types, and then the typical appearance of these materials just emerges automatically. So we no longer have to develop a specific model for this type of weave pattern, for this type of weave pattern. We just scan it and then get the result we hope for. So this is an example from the satin. This is for wool gabardine. And then this is for velvet, and we get this typical rim highlight that velvet has. And following this, we began working with the Rhode Island School of Design and developed a method that could take as input a weaving pattern for an industrial loom. And they were really interested in that because they actually have an industrial loom, and they have lots of students who want to use it. So especially as the semester ends, there's a long queue of people waiting to produce their results. And so if they had a sort of a preview, then maybe they could reduce the number of false mistakes. So here's an example of that for a jacquard brocade. All right. So far I've spoken mainly about appearance models, and I've focused on specific materials in isolation, but materials also interact with each other, and that's an interesting and challenging problem on its own. So in the last part of the talk, I'll focus on this aspect, and the project I'll discuss was published at SIGGRAPH in 2012, and it's also the topic of my PhD thesis. And the observation of this project is that whenever we have a light transport simulation, then geometry and materials are highly related to each other, and they give rise to another high-dimensional geometry that I'll explain now. And the problem we tried to tackle here is how to find specular light paths. So those are light paths which go from a light source to a camera, and then they involve one or more specular interactions. So an example of that would be a reflection in a mirror or a refraction in a water or glass surface. Now, the problem here is easy to see when we want to render this kind of a swimming pool scene. So we can shoot a ray from the light source that'll refract into the pool, and then it'll bounce around and eventually leave. But the problem is that to construct a complete light path, we have to exactly hit the aperture of the camera, or the eye here in this case, which has extremely, extremely low probability. We can also do it from the other way, so we can trace from the camera side, but then as we saw before, the probability of randomly hitting the sun is just low. It's a very bad sampling strategy. We can also try to come from both sides, but the issue is that we really want those to meet in a single point, so that doesn't work either. So this type of scene is surprisingly difficult to render if you want to get unbiased results. To understand what's making this so hard, we can analyze it on a bit higher level. So let's look at this very simple scene in flatland. We have a light source, a sensor, and then there's a mirror at the bottom, and I'm showing one example light path. And because everything is so simple vertically here, let's also forget just the y coordinates, and then we just parameterize that vertex by the x coordinate on the camera, then on the sensor, and then on the mirror. So now, for that to be a valid specular reflection, we know that the inclinations have to match. So theta 1 has to be equal to theta 2. That's just the law of specular reflection. And with our particular parameterization of the light path, we can also write that in another way, which is to say that x2 has to be exactly in between x1 and x3. So far that's quite tangible, but let's take a step back and think about what's happening here in a more abstract way. We have a light path with three parameters, x1, x2, and x3. So we can also think of it as a point in a three-dimensional space. And then this three-dimensional space is the space of all possible trajectories that light could take with one bounce. So with that in mind, let's look a second time at this equation. And you can see that it's actually a plane equation. So what it's saying is that those light paths that we care about and which satisfy the physical laws, they all lie on a plane which is kind of passing through this space. So that's kind of interesting. More generally, we can observe that actually whenever we have specular reflection or refraction, the subset of paths that we care about that satisfy the physical laws, they lie on a lower dimensional subset. So we can formalize this a bit. So for both reflection and refraction, we can write down a constraint which captures what it means for a scattering event to satisfy the corresponding physical law. And so on a light path with vertices x1, x2, and so on, that always involves three adjacent vertices. And then generally, if you have light that goes into a glass of water and then out on the other side, we'll have a few of those constraints. And so we can stack them up all together into a function C. That's kind of the combination of all these constraints. And then we want to basically set that to 0 and get what's left over. And so normally, this is what we call the specular manifold. And normally, when you do Monte Carlo rendering, you just throw darts on this manifold, which can be pretty inefficient in some cases. And what we want to do is to develop a rendering algorithm that can parameterize it and move around. So we really build into this geometric knowledge into the rendering algorithm. So I'll just show one brief example here for a glass sphere and a mirror reflection at the bottom. So we can take this function c that I mentioned before and differentiate it, and then we get the Jacobian. So I won't go much into detail, but basically what it tells us is what happens with all the other vertices when we wiggle around one of the endpoints to first order. So it's just an approximation. It tells us kind of how to keep that path in a valid configuration. And to make it usable, we also combine it with the second operation that's a projection onto this manifold. And so by combining both of those two, we get an algorithm that looks a lot like Newton's method. It takes linear extrapolation and projection steps on this manifold. And then if we put those together, we can modify this light path, and it remains in a valid configuration. And here's just a short video of what that looks like in practice in an actual algorithm. So we still search with brute force for light paths in these little squares, but then you can see that bigger portions of the image suddenly light up. They become brighter because we were able to explore the neighborhood of these light paths. So we kind of amortize the cost of this brute force search. And it works also for rough dielectrics, but I don't have time to go into that. So this was really a new operation, and that has been adopted by the community. So there are a number of papers now that use it. I think two or three more also this year. I'll skip over the next project because we're a little short on time. Okay, so I've presented several techniques that basically change some of the abstractions of the rendering pipeline to make realistic rendering more efficient. And the last change was the most extreme because we created this new tool of the specular manifold that kind of sandwiches itself between all of the other components. So this is the direction where I see a lot of promise in the future for solving some of the fundamental problems that still exist for this architecture. So returning from the pipeline from the beginning, it's clear that much remains to be done. So my dream is that at some point we'll be able to capture not just the shape, but really the appearance of objects easily in a few minutes and to 3D print them to create physical objects again. And I also want to work on these transformation tools to make them more intuitive to people who are really used to working with materials in their daily lives. So before I finish, I want to mention the Mitsuba renderer project. So this is a piece of software I wrote during my PhD, and it's a plugin-based system. So the idea is that these rendering systems are very big, and so it's an impediment when you want to work as a researcher in this area that you have to build this giant system before. And so here with Mitsuba, you can just work on one plugin, and then the burden becomes lower. And it also has implementations of many state-of-the-art techniques, which is convenient when you want to compare against existing methods. I'd like to acknowledge all my co-authors, without whom this work wouldn't have been possible. And I also want to thank my wife, Olesia, who made many of the 3D models in this presentation. And that concludes my talk. Thank you.
Great. We have time for questions. So about halfway through your talk, you were talking about a sequence of total internal reflections.
Mm-hmm.
The resulting light that comes out of the physical object at a different place.
That's right.
Where it goes in. Does your model allow for that?
No. So in this particular model, we assume that the layers are thin compared to the scale of things we're looking at, so that we can remove that parameter. That's actually very important just to reduce the dimension. Otherwise, the storage would become prohibitive. So what we're left then is a BRDF, which is 4-dimensional. That turns out to be still too much storage. So we focus on isotropic BRDFs, which are materials that still look the same if you rotate them around the normal direction. So then it's just 3-dimensional. And even then it's challenging. So there's a lot of kind of technical aspects of the representation. We have to go to frequency space and then exploit sparsity and do a few more things, and then we can get storage under control. So doing the spatial dependence, I think, is unfortunately not really feasible at the moment with that type of method. Yes?
You mentioned two things where basically artists have a more physical handle on things, like the weaving pattern example,
Mm-hmm.
and also the coating example, where I can have the gold layer and then some coating on the gold layer.
Mm-hmm.
And I can see that the artists there really can manipulate some physical sliders and feel very satisfied about these physical controls. Can you also imagine that there are things where going closer to the physical, detailed models is actually hindering the artist, or that is sort of at odds with the concepts that an artist or modeler has in their mind? So is it always a way that going closer to physics is going to be more easy to manipulate, or is there some challenge? And how would you address this, or could you think about addressing it?
So, for instance, this layered model that I mentioned just now, that's sort of the way that I think about materials in terms of their index of refraction, Beckmann equivalent roughness coefficient. So those are also not parameters that are very usable to I don't know, a goldsmith, for instance. So one thing you can do is reparameterize everything. There are some people who've been working on that, just finding more intuitive parameters. For instance, something that will let you move between diffuse and specular. There's a BRDF that's being used by Disney that does that. And so they have still a physically based reflectance model underneath, but all of the parameters are exposed through some map, taking as input artist-friendly parameters. So that's an option. Not sure if it's really usable for everything. In general, it's definitely the case that the more physically based you become, the harder you also make the modeling for yourself. So these rendering systems, they really require perfectly meaningful inputs. So you mentioned earlier that you had issues, for instance, where the normals were flipped on some model, and then the rendering you get out of that is just garbage. That's definitely the case. You have to really put a lot of, especially when you model things out of glass, there are changes of the index of refraction. The moment that your model is not watertight, or there's some kind of transition of index of refraction changes that doesn't make sense, you can actually add energy to you can make a little atomic reactor out of a glass of water that, like, every time light goes through, it increases in energy. And so I find myself explaining a lot of these things over and over again to people using the system, and maybe another interesting direction would be just to figure out how to make things more resilient. And yes?
The Saturn, to me, looked like it was begging to move.
What do
there's
you mean?
obviously a whole different, part of computer graphics in terms of accurately simulating the motion of a Saturn cloth.
Okay.
Is it completely orthogonal to what you've done, or do you think some of these ideas could possibly be used in the simulation of motion, at least at a fine scale?
So at Cornell, there's a big effort, or used to be a big effort, on cloth simulation, especially these types of woven pieces of cloth. That's where this scarf example, for example, came from. It's not really related to light transport, I would say. There are some material parameters that could probably go into both models. So if you have something that's kind of very fussy, that will have a visual effect, but it'll also have an influence on the dynamics of the material. In terms of the actual simulation that has to happen, I think it's rather different. One is a steady state simulation. In the light transport simulation, we really don't care about time because light is moving so fast. We can just remove that variable.
You skipped the project.
Oh yes. So I'll just give you a brief idea what's happening here. So this is published by now. Sorry. So I mentioned that rendering is very expensive, and part of the problem here, making my way slowly. Okay. Part of the problem is that the amount of pixels that have to be rendered is just very large, and this is becoming worse and worse with the increases in pixel resolution. So in the movie industry, 4K is now becoming very predominant. Nobody can render 4K images. It's just too expensive. Then you have to do it for stereo. And now there's also a trend to move to higher frame rates. So from 24 frames per second to 48. So there's just no way. And so how can we deal with that? Well, one thing that people often do is to use the coherence in these situations to reduce the burden. So because all of these frames are so similar, you could just render a subset of them, maybe every fourth one, and then reconstruct what's missing in between. And you could render the images at a lower resolution and then extract do some kind of upsampling. And then also you could render noisy frames and post-process them with a denoising filter. And you can also do all of these 4 things at once. Now the problem is that there are certain assumptions of these 2D post-processing algorithms that really don't work anymore the moment you have renderings with a realistic light transport simulation. And that's because each pixel captures many different effects. So you might have an object that's maybe going this way in screen space, but the object is specularly reflecting, and the reflection is actually going that way. And maybe it's not just reflecting, but also refracting. And you have yet another thing that you can see in that pixel, which is a refraction path that's moving yet another way. So you have all these conflicting things that are reduced to 2D, and then you cannot process them with, I don't know, basically any kind of state-of-the-art technique. So what we did here is to instrument a rendering system so that it generates many different images that separate out all of those different effects that are happening. So you can think of it as generating some kind of a tree that you can see here, and all of the leaf nodes are images, and then the tree nodes are operations of what you do with these images. So maybe you add them or you multiply them, and the important thing is that all of the leaf nodes capture such specific physical effects that you can now suddenly run 2D post-processing algorithms on them. And then we also determine where something that's visible in one frame goes in the next frame. So here's just an example. So we start with something that's very low res and noisy and subsampled in time, and then we extract a fluent animation out of it. So it kind of seems like magic, but what is hidden here is that we render out a huge amount of information. So our images have, I don't know, 100 channels or so. We started initially with images that were 1 gigabyte in size or so. Later we managed to restrict ourselves a bit more. And so one challenge here is also that some of these refraction paths can be quite elaborate. So here you can see these refractions through a vase. And if we just interpolate the motion based on the objects of what's visible in screen space, we get all of these artifacts. And so using similar techniques to what I mentioned before with this specular manifold, we can actually compute the screen space motion of specular paths. I think that's called specular flow by some communities. So that's basically what this project does.
Okay, so let's thank Wenzel once again for a great talk.
Thank you.